Okay. Okay, it looks like things are working now. So what I prepared for today is, I would say, F equals MA level problems. And then I'll appreciate your feedback as to whether it was too easy, too hard, and then I can adjust accordingly.
Thank you.
So let me share the screen. Yeah, just give me a second. Okay, folks. Do you see the whiteboard? Okay, let's start with some warm-up problems. Sounding. Okay. Okay, problem A. Two cyclists go around the circle, stadium, of 400 meters. And they meet each other every 20 seconds. That's the circumference. Okay. So they meet every 20 seconds. And we know that we're given that one cyclist goes 1.5 times faster than the other. Find each cyclist's speed. Okay, that's right. Which one is which though? Uh-huh. Okay, correct. Do we need to discuss it or everything is clear? Okay, so let's do another one. Warm-up number B. Again, tell me if you already know this problem because it's pretty classic, but if you don't, that's a fun problem to do. I'll call it a crazy fly problem. There are two trains. You know that one? Yes, yes. Yeah, well, let's do it real quick then, okay? So the first train goes with V1, the second goes with V2. Given V1, let's say 20 kilometers an hour, V2, 30 kilometers an hour. The distance between the trains is, say, 100 kilometers. Now the fly has a crazy speed of 40 kilometers an hour. So yeah, you know the story, right? The trains start moving simultaneously, and the moment the trains start moving, the fly wakes up and starts flying toward the second train. It hits it, turns around instantaneously, and goes back. Then it hits the first train again, turns around. So the fly keeps flying at a constant speed v until the trains meet. Okay. So find the total distance the fly travels by the time the trains meet. $80. Does anybody want to explain? Okay. Yeah. Okay. Let me write it down. D over V1 plus V2 is 2 hours. That is the time to meet, right? And then the fly Okay, that works. It looks like a lot of you knew the problem, right? Yeah, there is a funny story behind this. Do you know who John von Neumann was? Let me write it. John von Neumann. Yeah. The guy who built the first computer, a very famous mathematician, but he was also a physicist. So there was a discussion as to what he's more, a physicist or mathematician. And they decided to test him by giving this problem because they thought, okay, a physicist would do it the way you just did, guys. A mathematician would like consider the infinite series of all the distances the fly covers and add the series. And so they asked him a question, and he answered like next second. So they thought, oh, okay, he's probably a physicist. And von Neumann, like, how do you know? Why? He said, well, here's our idea that you answered so quickly. You must have done it this way, and this is the physics way. He said, oh, I summed the series. So check out this guy. He wrote a really great book, The Computer and the Brain. It's pretty interesting. Okay, so looks like you are warmed up. Let me start asking some deeper questions. So today we'll focus on just one-dimensional motion. And I know not everybody here has taken calculus. Is that correct? Okay, well, we won't need calculus in principle, but it helps if you're comfortable with calculus. Okay, so let me do this. Yeah. You know this problem? Ah, well, this is, well, we'll see. Okay, let me ask you, and if it's quick, we'll just move to the next one. So, a student obtained an equation for, where can I write? Yeah, here. A equals K minus BV for a certain motion, where K and V are positive constants. Okay. Which of these graphs would be consistent with this equation? And why? Oh, I'm sorry. I meant B. Yes. Yeah, my bad. So yes, K and V are, and V obviously not. V is the velocity. A is the acceleration. A. Okay. Can somebody explain why? Well, I know some of you can integrate, and that's what I meant when I said it helps. But this problem can be solved without using calculus. Just understand the concept that acceleration is the slope of velocity graph. Just to be clear, everybody paid attention that this is v versus t, right? B. Well, before we jump to B, can somebody explain why A cannot be correct? The reason is actually not physical. It's purely mathematical. Why A or even C, for the same reason, cannot be correct. Oh, that's an interesting. Okay, that's a good reason. Yes, that's nice. So there is another reason. Even if you lift these graphs up, so they never have zero velocities, these graphs still don't work. And here is the reason. So when you have a specific value of v, that determines a specific value of a through this equation, right? But what do you see on graph A or C? That if you pick a point somewhere here, pick a point somewhere here, and say here, same value of v, right? According to the equation, you should have the same acceleration. And these 2 points may work fine, but if you look at like this point, which has the same v and should have the same acceleration, it has a negative acceleration. Same situation is here, right? You pick points of the same v, but they have different slopes, different accelerations. Make sense? Yeah, so this is the reason why A and C don't work, and in fact, the graph has to be monotonic. So you're saying B. So I heard some suggestions to actually use calculus. Well, okay, so let me write it, and something that you can do at home as a homework. Yes, you can totally say that this is equal dv dt. Okay, and then solve this equation. So the way you would solve it would be this. You would say dt equals dv over k minus bv, and then integrate both sides, right? What I just did is called separation of variables. So you integrate both sides and then express v as a function of t. So this is doable. That's not super hard, but we can actually do it without calculus. So this is your homework to finish this approach. So are you guys still debating between B and D? Uh-huh. Okay. Is everybody okay with that point? At least that the D and E are ruled out. Uh-huh. There has to be an asymptote, and it looks like B does. Okay. So I think that's pretty strong logic here. So yes, that's right. B is the answer. Anybody has any questions about this problem? Oh, okay, so got another one. Which may be simpler. Oops. Okay, so this is the situation. Which of these graphs best represents velocity versus time of an object moving through the air? The object originally moves straight up. Do not ignore air friction. Which one? B. So you throw the object up and then it approaches zero velocity. That does it freeze in the air? D. Okay, can somebody argue? Okay, okay, very good. Yep. Just to add, I'm not sure if I heard you correctly, but when the object moves up, air resistance is there as well. Yeah. Okay. Good. Good. Let's move on to the next one. Okay, this is an interesting one. So what have you seen this before? Yeah. So this is a bunch of beads on a string, and one tick mark is 5 meters. Okay. It's 5 meters. So each of these strings is dropped on the floor. The question is, which of them would result in an equally time-spaced sound? Okay, let me just check. Is everybody agreeing with that? Okay, quadratically then. And which of them does that? So you're talking about which one? D. D. Okay, gotcha. Yeah. So as you probably know, if we assume that G is approximately 10 meters per second squared, then in 1 second, we have 5 meters, right? Something drops over 5 meters. In 2 seconds, it drops by how much? Right? And in 3 seconds, well, I mean, if you're counting fast, then probably yes. Okay. Yeah. Let me just put it down here. Okay. Yeah. And if you convert this to tick marks, this would be 1, 4, 9, and that's what it does, right? 0, 1, 4, 9. Okay. So in case you didn't know, so yeah, you did it quickly, but let's learn something from it. So in case you didn't know this problem and you didn't have a chance to think until somebody already said the answer. So this is what I want you to take home from this problem. So think about how would you approach this problem if you just didn't know how to, like if you didn't know this solution. And my suggestion would be to look at, for example, B, which has equally spaced beads, and just see what happens. So if you just drop equally spaced beads, yeah, we know it's the wrong answer, but what kind of sound sequence would they produce? Okay, great. So not only does it tell us that B is wrong, it also gives us a hint as to how they should be spaced, right? So if you push this idea further, you can argue, oh, okay, so if the beads move faster and faster with height, that means they need to be spaced more and more, right, as you said. So you would be eliminating, for example, 8 as well. And then you would need to focus on C, D, and E. And well, eventually we'll have to come up with the quadratic scaling, right? But at least this is how you would start thinking about this problem. Remember, on the test, if you can eliminate one or more solutions, you're in a better position because at the end you can just guess. If you cannot figure it out, you can just guess from fewer options. Any questions about this? No? Okay, let's move on. Something about non-constant acceleration. Actually, let me ask you an auxiliary question to this. No, so what I'm going to ask is not actually related to this graph yet. Okay, yeah, let me just read it. So if you, yeah, ignore this graph. Two cars start at the same position with the same speed, v naught. Car A travels at a constant speed. Okay, VA is just v naught, but B decelerates at a constant acceleration A. And this is negative. Okay. At the instant when B reaches speed of 0, what is the distances? What are the distances traveled by A and B? Oh, sorry, what's the ratio of distances traveled by A versus B? So by the time the speed of B reaches 0, what is the ratio of distances covered by A and by B? So dA over dB. When VB is 0. Yeah, this was not meant as a hard problem. So does anybody have some thoughts? Hmm. Are you guys trying to sketch a graph of how this looks? And which graph would be helpful, actually? What's that? Yes, velocity is usually the most helpful graph because you can extract information about both position and acceleration from it. So let's do that. Let's sketch velocity versus time graph, and let me mark V naught here. So what does the A graph look like? Okay. And B graph? Yes, yes. Yeah, did I not make that clear? Yeah, they both start at the same speed, but one keeps constant, one goes down to 0. So these are the graphs. And then as you know, the distance is represented by the area. We need to find the ratio of two areas, and that ratio is what? Yeah. What's the ratio of areas? Okay. Well, the way I wrote it should be 2. But yeah, you got the idea. So yeah, the rectangular area is obviously twice as much as the triangle one. Okay. So this is still constant acceleration, but the next problem will be about non-constant acceleration. So yeah, let me try to read it carefully then, or slowly. So if you start from rest and accelerate to a given final speed v naught after time t. So you're given certain speed v naught and the time during which you accelerate. And again, it's not specified whether it's constant acceleration, non-constant acceleration, could be anything. Okay, but it's always non-zero, or well, it's actually non-negative. Let's say non-negative acceleration, maybe positive, maybe 0. But again, not necessarily constant. So if d is the total distance traveled, what is the range for the distance? So it's not that it's really given, but d is the distance. Okay. Do you want me to repeat it? So you start from rest, right? Let me put it here. The initial is 0. You start from rest and accelerate with non-negative acceleration until you reach v naught. The time it took is t. What is the range? Like in what range is the distance traveled? What is like the minimum distance and the maximum distance with this data? Yeah. In other words, find d min and d max. Oh. Okay, so you're saying the d min is 0, right? Did I get you right? And max is okay. So yeah, well, let's just make sure. How's everybody else? Are you guys following? Yeah. So let's just illustrate that what you described by hands. We'll try to record. So this is t. This is v. We know the time is capital T. The final velocity is v naught. So this is where we need to get. So this is our final point. We start from here, and basically our motion can be described by some kind of curve in this space. Notice acceleration is never negative. That means we cannot overshoot, right? We always go up, or at least we never go down. Okay, that's important. So we're basically confined within this rectangle. And then, as you correctly said, the minimum area would be if you basically go at 0, 0, 0 speed, and then at the end you get a kick. So you jump to this final speed, but really you cover essentially 0 distance. Make sense? The other extreme is when you get that kick right away, and then you just keep constant velocity. Then your area is pretty much all of the rectangle. Okay? So yes, indeed, this is correct. So you see distance can be quite different depending on how acceleration is set up. Okay, good. Well, yeah, let's do those problems that you saw. Okay, so yeah, let me explain what this is about. The velocity as a function of time is given by the graph that you see. What is the total displacement of the particle in the interval from 0 to 1 second? So what is the displacement from 0 to 1 second? What's that? 1/2? Can some 1/2 meters. Okay, so let me put it here and we'll analyze it. Delta x equals 1/2 meters. Okay, can somebody elaborate? Okay. Okay, yeah, that was it. So let me try to give you something harder. That was too easy. Okay. How about this? Ignore this mark. That's it's not right. So what's the difference between this graph and the previous one? This one is versus position, right? Okay, so let me, like, do you feel you have enough data? Yeah, you need some information here, right? So let me tell you some more things here. Let's say the particle starts at t equals 0 and x equals 0. So when the clock starts, position is at 0. And then you wait for 1 second, want to find the distance the particle travels. Yes, this is the starting point. Yes, and t final is 1 second. What, how about that? Okay, what does everybody else think? Okay, guys, yes, that's right. Yeah, this was a tricky question, but good job catching that. Yeah, this is a non-typical graph, right? This is velocity versus x, not something that you normally see. So if you start at 0, that means your velocity is 0. Don't move anywhere. You stay at 0, and velocity stays at 0. So nothing really happens, okay? The particle is stuck at 0. Okay, so let me update this a little bit just to make it non-trivial. Pretty much the same question, but a different graph. So let me display that. Okay. So I'm giving you multiple choice question. So this is the new graph. You see it's shifted up now. So it doesn't start at 0, it does move. The question is, which of the 5 graphs below correctly represents v versus t? Again, calculus may help, but I think you had some good thoughts there. So can somebody just summarize what you've come up with? Okay, exponential meaning which graph? D. Okay. What does everybody else think? I'm just curious. Yeah, I'm not sure if I can hear you okay. Yeah, D is the right graph. So, and the logic is correct as well. So just Andrew is right. You need to clean it up a little bit. Just understand what's cause, what's the effect here, right? So yes, first you look at the given graph and notice that in the very beginning there is already some positive speed, right? And that means the particle is moving. X increases. Now from the same graph, as X increases, so does V, right? So V increases. That eliminates A and B, for example, right away. Now, does it increase at a constant rate? Let's see. So as V gets larger, that means X increases at a faster rate. And if X increases at a faster rate, that means V increases at a faster rate. So as time goes on, the V increases faster and faster. That eliminates this, which is a constant rate, and this, which is a decreasing rate. You don't have to know that this is exponential. It is exponential. If you do the calculus, you'll find that this is an exponential. But again, you don't need to know that it is. Just need to know it's an increasing rate. So this is actually another homework question for you folks. Use calculus and understand what kind of function v of t should be. So well, I should probably say calculus. It's really more like a differential equation question, but it's a simple one, much similar to the one we did. Okay. Okay. So you can say that v of x is some, let's say, v naught plus kx, where v naught is a positive constant, k is a positive constant, and then that will allow you to get the velocity. Okay. Now I basically have just one last problem. It's a long one. You may want to just extract information. I'm not sure if you'll be able to like solve it on the spot right away. So if not, then we'll just discuss some general ideas and you'll finish at home. Okay. So on the river coast, there is a port. So there is a port. A barge is going down the river at the same speed as the river flows. Okay. At the same moment, the barge passes the port. A motorboat departs from the port to a village at the distance 15 kilometers down the river. So this is port. This is village. And this is, say, S1, 15 kilometers. Okay. The motorboat reaches its destination after 45 minutes. So it's a faster thing. Okay. Then it turns around, right away and starts immediately moving back towards the starting point. At distance S2, it meets the barge again, the second time. And S2 is 9 kilometers from the village. Okay, 9 kilometers from the village. Okay, so you want to find two things. The speed of the boat with respect to the water. Motorboat with respect to the water. And the speed of the river or of the flow itself. Does that make sense? So did you capture everything? Yes. And the river's speed is also unknown. No. It's one same motorboat. So first it goes down the stream, hits the village, turns around, starts going up the stream, and meets the barge again. So by the time it does that, barge will be somewhere here. Yeah, so the barge just goes with the speed of the river. Okay, flow. Yeah, folks. So one approach is by brute force. Just write down all the equations you can and then do the math. Is that what you're probably doing? Okay. that'll probably get you the right answer. And now there is a neat approach. So how about this? I'll give you a hint about the neat approach, but you do both and then you compare. And next time we'll just check how you guys did. So how many of you are familiar with relative motion? Okay, so it's actually pretty handy in this problem. So I suggest you consider this problem in the reference frame associated with the barge. Consider the reference frame of the barge. Okay, so imagine you're a passenger on the barge. And let me just give this one hint and see how far it takes you. So let me just summarize. So your homework is finish this problem and the other ones I mentioned. Finish this problem using the hint. And compare it to the brute force solution. Like everybody knows what to do in this approach, right? Like what equations to write. Yeah. Okay. So why don't you do both, and then we'll check how it went. Did you capture everything from the screen? So okay. So, okay. Yeah, let's pause here. Folks, tell me, I got an impression most of the problems were too easy for you. Is that accurate? Okay, graphs. Yeah, let me take record of that. Okay. Do you feel we're ready to do two-dimensional motion next time? Okay. And Andrew, can I ask you to maybe make a raster, like names and pictures of people who are present or would be present, like yeah, I'm trying to read what it said. What's that? Oh, Evgeny Gorbachev. Okay, nice to meet you. Okay, folks. So next Tuesday, are we aiming at 3 o'clock? Three to 5. Okay. So I'll see you then. Have a nice weekend. Bye.